A rational function is something like this. It's a function where in the denominator there are some x's, maybe something like this. In the numerator there can be x's also. And graphing a rational function can be kind of complicated, so I want to take you through certain patterns that happen when we're trying to graph rational functions. This isn't in the exact form of a rational function. It could be expressed as like f of x equals 9 over x. But I like it in this form because we get a feel for what's going on. If I were to make a list of like pairs that make it true, 1 times 9 is 9, 9 times 1 is 9, 3 times 3 is 9. Also, negative 1 times negative 9 is 9, negative 9 times negative 1 is 9. And if I were to graph all these, it looks something like that. And the full picture looks like this. These are two branches of what's called a hyperbola. And notice that if you pick something really close to 0, like 1 over 100, you would need a really big y value to like make up for that. And that's why we get something called a vertical asymptote in the y-axis. On the other hand, if you pick some really big number like x equals 900, you would need a really small y value to make up for it. And that's why we get another asymptote, which would be a horizontal one on the x-axis. So asymptotes are these dotted lines that we draw. They're not actually part of the graph, but they tell us that the graph gets closer and closer to that without ever touching it. A hyperbola has a center, although the center is not an actual point on the hyperbola, but it's in this case where the two asymptotes intersect. And a hyperbola also has two vertices, and in this case they are at 3, 3, and negative 3, negative 3. Take the square root of 9, it kind of tells you that you'd have to go 3 to the right and 3 up to get to the vertex, and 3 to the left and 3 down to get to the other one. F of x equals 1 over x is our most basic hyperbola. If the denominator is 0, we say it has a vertical asymptote at the number that makes the denominator 0, which in this case is 0. So we can draw that in. Now, because the numerator is a constant, then the bigger the denominator gets, the numerator stays the same, and the larger the denominator gets, the smaller the fraction gets. So that's why it has a horizontal asymptote is at y equals 0. Now, this 1 in the numerator tells us that the vertices are going to be here and here. That's 1 to the right and 1 above the center, and 1 to the left and 1 down. So 1, 1, and negative 1, negative 1. Also, we're going to have horizontal asymptote, y equals 0, but for positive x values, even though this thing's going to get very small, it's going to be still positive. And if you put a big negative number in, this 1 over x is still negative, and that's why we have sort of going from above towards the asymptote here, and here from below. Now, when I put a small positive x value in, I get a large positive y value, and that's why we get an arrow like this. And if I put a small negative x value, I get a large negative y value. And when you connect up these things, you get, it kind of looks like an L. You get this hyperbola. There's some terminology for talking about asymptotes that you see in calculus a lot. It looks like this. they say like the limit as x approaches infinity of 1 over x equals 0. So they put a little plus here to say it's above 0. It's 0 from the positive side. And the limit as x goes to negative infinity of 1 over x is also 0, but put a little minus there to say it's negative. Close to the vertical asymptote, this red line, we could say the limit as x approaches 0 from the right of 1 over x is going to be positive infinity. But when we approach 0 from the left, that minus there, 1 over x, is negative. Now, this is ways of describing these sort of arrows, but with symbols. This plus 3 causes a vertical shift up by 3 units. So it happens that the asymptote is no longer, the horizontal asymptote is no longer the x-axis, but it's at y equals 3. But the vertical asymptote is still at x equals 0 because 0 is the only number that makes this undefined. And we get the same picture as before. It's shifted. Now we have something that hasn't happened before, which is we have a intercept. The other two didn't have intercepts, but this does. And we can actually work out what it is by saying 0 equals 1 over x plus 3, negative 3 equals 1 over x. X is equal to negative 1/3. So we have this negative 1/3 comma 0. If instead the plus 3 is in the denominator, well, in this case, the x plus 3 equals 0 when x is negative 3. So negative 3, x equals negative 3 is going to be the vertical asymptote. But the horizontal asymptote is going to be y equals 0 because the numerator is constant, the denominator is getting bigger and bigger, so it's getting closer and closer to 0. And we're going to have something like that. This one has a y-intercept, and we can calculate that by doing f of 0 equals 1 over 0 plus 3 equals 1/3. So 0 comma 1/3 is the y-intercept. And this one has a whole bunch of things going on. This minus 3 means that the horizontal asymptote is down here at y equals negative 3. This x plus 2 means that the vertical asymptote, what makes the thing undefined, is at x equals negative 2. Now this 4 here, it doesn't do a lot to the graph, but what it does do is it makes the vertices sort of 2 to the right, square root of 4 is 2. So if I go 2 to the right and 2 up, 2 to the left and 2 down, I get my vertices. And this picture has a y-intercept and it has an x-intercept. When there's a negative out here, well, this plus 2 gives us our horizontal at 2. This minus 4 gives us our vertical at 4. Now the minus sign flips it upside down, so now the branches are going to be, instead of here, it's kind of like quadrants 1 and 3 of, if you think of these asymptotes as like axes. Instead we're going to be in quadrants 2 and 4 of those. So that's what happens when you have a minus sign there. Now this looks a little different, but if we split it up, 4 over x minus 3x over x equals 4 over x minus 3, we find that it's just like before. It's got a horizontal asymptote at y equals negative 3. It's got a vertical asymptote at x equals 0. The 4, again, it doesn't do a lot, but it means that these points here are sort of 2 to the right and 2 above and 2 to the left and 2 down. Now for this one I'm going to introduce a new concept that's going to be really important in the next couple of videos. It's called a sine chart. And what a sine chart is a number line, and on the number line we mark off what are called critical values, like -5 and +1. Those are values that make the -5 makes the numerator 0, the +1 makes the denominator 0. You put a 0 over the -5 because if you plug 0 into the function you get 0. But you put a u over the -1 because 1 over the +1 because 1 makes it undefined. Now, there are 3 intervals we have to look at now. Numbers bigger than 1, numbers between -5 and 1, and numbers less than -5. If you take any number bigger than 1 and plug it into this function, the numerator is going to be, like if I put 2 in, I get 7 for the numerator, and I get 1 for the denominator, which is positive. It's going to be true for any number bigger than 1. Anything bigger than 1 is going to make both of these terms positive. And if I pick something really negative, like -10, -10 plus 5 is -5, -10 minus 1 is -11, is -11, negative divided by negative is positive again, so we put a plus there. But for numbers in between -5 and 1, the x plus 5 is going to be positive, and the x minus 1 is going to be negative, so the quotient is going to be negative. This thing is called a sine chart, and it's going to be really useful. Let's see how we, it tells us a bit about what the graph looks like, what to expect. We can see that there's going to be an asymptote at x equals -1. This u here tells us that. So I go to -1 to make that asymptote. Sorry, it's not -1, it's at +1. But otherwise, we don't really know exactly. Well, we know one other thing, which is that this point over here, this 0, means that there's a point on the there's an x-intercept at -5. While we're at it, we can put 0 in. We can figure out f of 0 by plugging 0 into this, and we get 5 over -1. That might be useful, just to know that 0 or -5 is the y-intercept. But here's how we continue with this graph. If we have a rational expression like this, we could divide the bottom into the top with long division, get 1, x minus 1, subtract these. 5 minus -1 is 6. So we get remainder 6. I'll write it as plus 6 over x minus 1. So our original function could actually be written that way. I'll put the 6 over x minus 1 first, the remainder thing plus 1. And we can see that this is what we've already done. This plus 1 here is going to be the horizontal asymptote. And the 6 is positive, so we can expect to be here in these two sort of quadrant type things. We have this x and y intercepts, so those are useful. If you look at the sine chart, you can see that it agrees that this plus means that it's above the axis, which it is, from -5 and to the left. This minus here means that from -5 to 1 it's below the x-axis, which it is. And this plus here means that beyond, to the right of 1, it's positive, which it is. So this really is just a fancy way of saying this, which we already knew how to graph. Anyway, sine charts are going to come in handy in the next video, but for now this one's over.